When you hear the word capacitance, you probably pictured this. Two metal plates separated by an insulator. But have you ever wondered why? Why this shape and not two spheres, an open switch, or even two disconnected wires? Because believe it or not, all of these are capacitors too. The only difference between them is how good they are at being capacitors. It was once I realised why they are different that the concept of capacitance finally made sense to me. So in this video, I want to show you exactly what changed my understanding and demonstrate what capacitance really is. To start with, let's establish the basics so we know exactly what our so-called textbook capacitor, known as a parallel plate capacitor, actually does. When we connect this to an external power source, charge cannot flow, so it builds up in the conducting plates. One plate becomes positively charged and the other negatively charged. If we then disconnect the power and connect the plates to a circuit, all that charge rushes back in a brief but very powerful burst. This is how things like heart defibrillators work. They release a stored burst of charge from a capacitor to jolt the heart back to life. A battery would not be able to do this. So how do we measure how good a capacitor is at doing this? This is where the capacitance comes in. The capacitance is a measure of how good the capacitor is at storing and releasing charge. However, the amount of charge that builds up on the plate depends on how strongly the charge is being pushed there. That push, of course, comes from the battery voltage. If we were to recharge our plates at a higher voltage, the charge stored in our plates would be greater. So the amount of charge stored depends on this voltage. A more useful quantity to measure is the voltage drop across our plates. When a capacitor is fully charged, this voltage drop must be equal to the battery voltage, at least in this circuit where there's just a capacitor and nothing else. When we discharge our capacitor, we can see that the plate voltage diminishes as the charge diminishes. Therefore, we define the capacitance as the amount of charge in each plate per volt across the plates. Interestingly, it turns out that this ratio is constant for any given capacitor, besides a few extreme scenarios. The larger the capacitance is, the more charge can be stored in each capacitor plate, per volt across it. But that raises an interesting question. What actually determines what this ratio is? What makes Q large or small for a given voltage? To understand this, we need to look a little more closely at what's going on between the plates. What we need is a quantity that somehow relates the charge in the plates to the voltage across them. This quantity is of course the electric field, which is basically a middleman between charge and voltage. If you're not familiar with fields, in part 3 of this series I introduced them visually, but to cut a long story short, any charged object generates an electric field around it, which is basically an invisible map showing how another charge would act if placed near it. In this case, our capacitor plates are charged, one positive and the other negative, so there is a field pointing from the positive plate to the negative plate. This is the direction a positive charge would move if placed between the plates. I want to stress that you can always make a good guess of what the field looks like intuitively, by simply sketching lines from the positively charged objects to the negative objects. So how does this relate to both the charge stored in the plates and the voltage across them? Let's think about it intuitively. Firstly, if we pushed more charge onto the plates, we'd logically expect the strength of the electric field to increase. We'll denote this in our diagram by increasing the density of field lines. I'm aware this is a bit vague, so we'll clarify this in detail in a moment. Now back in lecture 4, we showed that the magnitude of the voltage across a path is equal to the integral of the electric field along that displacement. In simpler terms, this is just the area under the graph of the electric field versus distance curve, going from one plate to the other. So, if the magnitude of the electric field increases, the area under this graph increases, so the voltage must also increase. Of course, the electric field can only increase here if the charge on the plates increases, so this does not violate our constant ratio between Q and V. More charge in the plates means a stronger electric field, which means a larger voltage. This is a very powerful relationship, as it shows clearly that all these variables are directly related to one another. Now we already have the exact equation linking the electric field to the voltage, which we'll write here. I will note that technically the voltage is minus this integral, but in the context of electronic devices like capacitors, we often remove it. But how does the charge in the plates relate to the field? To answer this, let's look more closely at the charge in our plates for a moment. The first question we might ask ourselves is, where even is this charge? Well, as we know, charges of the same sign repel each other, so when we charge our plates, they want to get as far away from each other as possible. The only way they can do this is to move to the surface of our charged object and evenly spread out over it. This might seem quite obvious, but this is actually an extremely important law of electrostatics, so it's worth stating it clearly. It allows us to say that the charge Q lies on the plate area A. But how does this relate to the electric field? To answer this, we'll use one of the most beautiful ideas in all of electromagnetism, Gauss's law. We won't explicitly derive the law here, but instead work through it intuitively. Let's add back in our other plate and draw in our field lines once again. Imagine now that we draw an invisible surface between our two plates. As we can see, the field lines shoot out perpendicular to our plates, such that they go straight through this imaginary surface. The number of field lines passing through, or more precisely, how much of the field passes through, is what we call the electric flux. If the field is perpendicular to our surface, it goes straight through, giving a large flux. However, if we tilt the surface, the field no longer passes directly through, as it goes through at an angle. In other words, the electric flux through the surface depends on both how strong the field is and how perpendicular it is to the surface. Mathematically, this is the dot product between our field vectors and the direction normal to this surface. This dot product might make more sense to you as the field magnitude times the area magnitude times the cosine of the angle between these two vectors. When the field lines are perpendicular to the surface, the flux is maximised, as theta equals 0, meaning cos theta equals 1. But if the field lines are not perpendicular, theta increases, so cos theta decreases, and accordingly, the flux decreases. Now let's consider enclosing the entire charged object in a surface, which we'll do using a parallelogram. Most of the time, the flux varies as we go across our surface, so we define the total flux as the sum of all the tiny chunks of flux over this entire surface. This is simply the surface integral of the dot product between the field and each tiny chunk of area dA. So why is this quantity relevant? Well, the punchline of all this is that Gauss found the total flux through the surface to be directly proportional to the total charge in our plates. In fact, no matter how weird or complex this surface is, as long as it completely encloses our charged object, the total flux is equal to the charge enclosed divided by the permittivity, which is just epsilon naught for free space. This is Gauss's law, and it relates the charge in our plates to the electric field it generates. Don't worry if it seems a bit abstract or intimidating right now, as we'll see in a moment that its meaning is actually quite straightforward. But let's return to our diagram from before, which we can now complete by writing out Gauss's law. If we return to our formula for the capacitance, we can now substitute Q and V with our new equations, which are entirely in terms of the electric field. I'm aware that this now seems much more complicated than it did before, but we're going to see that writing a capacitance like this tells us a lot more about what it really is. Let's ask ourselves a simple question. How would we maximize the capacitance based on this equation? Well, the simple answer is that we want to maximize the numerator and minimize the denominator. To maximize the numerator, we'll need to maximize the electric flux between our plates. Looking at our equation, there are three ways we can do this. First of all, we can maximize the field strength between our plates, such that we get a higher density of field lines. We'll come back to how we'd actually achieve this in a moment. The second thing we can do is maximize the total surface area of our plates, which results in more field lines and therefore more flux. Finally, we want to keep the field lines as perpendicular as possible to our area. In other words, we want the field to be as uniform as possible, going straight from one plate to the other, with as little divergence as possible. Let's now try to minimize our denominator. There are two things we can do here, but there's some clear competition with our first 3 points. To minimize the denominator, we'd actually want to minimize our field magnitude, but obviously we've already tried to maximize it. So in fact, increasing the field strength increases the numerator and the denominator, so its effect cancels out entirely. The field strength, therefore, does not affect the capacitance at all. The capacitance is completely independent of it, and this actually makes complete sense because the only way to increase the field strength is to add more charge, and the only way to add more charge is to have a larger voltage. So we can cross this requirement out entirely. Still, we can also minimize the denominator by minimizing the path length of our electric field lines, which can obviously be done by moving the plates closer together. All in all, we are left with 3 conditions to satisfy if we want to maximize capacitance. This is rather interesting as it means that the true fundamental decider of capacitance is not charge or voltage or even electric field strength, but the geometry of our system. This includes the shape of the conductors, the total surface area, and the distance between them. Let's return to our examples at the start to demonstrate what this means. First, let's talk about the shape of the field, which depends entirely on the geometry of the system. In the case of parallel plates, we get an almost uniform field where pretty much all of it goes straight from one plate to the other. On the other hand, for our 2 charged spheres, the field looks more like this. Clearly, it is all over the place. Only a small part of it right between the spheres actually goes straight from one sphere to the other. This is why we don't design capacitors like this. So let's focus on our parallel plates for a bit and return to our capacitance equation. In this case, the maths is actually really easy. There is some deviation of the field at the edges, but we usually ignore this as its effect is quite minor. For the numerator, all the field is contained within the plate area and goes straight through our imaginary parallelogram. So, the field is always perpendicular to this area, which is equal to the total surface area of the plates. Therefore, our integral is just the magnitude of E times the total plate area A, times the permittivity, of course. The denominator is just as simple. In this case, each path is directly from one plate to the other, so this integral is just the magnitude of the field times the magnitude of the path, which is just the plate distance. As you can see, we have the field magnitude in the numerator and the denominator, so we can just cancel it out. We are left with this equation for the capacitance of our plates, and if you study physics at even a pre-university level, you'll probably recognize this. Hopefully, this is a somewhat satisfying moment to you, as we finally come back around to something very neat and simple. All in all, we transformed our C equals Q over V equation directly to this, which finds the capacitance entirely in terms of the geometry of our system. This is what actually determines capacitance. Of course, we can apply our equation to other system geometries too. While researching this video, I actually stumbled across a surprisingly comprehensive list of equations for capacitance on the Capacitance Wikipedia page, and as you can see, these are far more complex than what we just did, and it would probably take me a whole other video to even do one of these. Still, if that is something you're interested in, you can always let me know in the comments section. But let's get back to our simple parallel plate system, because there's actually one more factor we haven't yet talked about. We haven't considered what lies between our 2 conductors. So far, we have just been treating this as empty space, so in our capacitance equation, we have written the permittivity as epsilon naught. However, if the space between our plates is not empty, we rewrite the permittivity as the relative permittivity times epsilon naught. As this lies on the numerator, if the permittivity increases, the capacitance will increase. But why is this? Well, as this material is an insulator, charges cannot flow inside it to completely cancel out the field. But these charges aren't completely static. These charges are in fact able to shift slightly, and when a field exists, they do this to minimize the field as much as possible. This is almost like a cheat code for capacitors, as a high permittivity literally scales up the capacitance by orders of magnitude. That being said, there is a limit to how large we can make the permittivity. If it actually approached infinity, our insulator would just become a conductor, and charges would be able to move freely. But even way below this, the constant can vary under certain conditions, such as heat, so in practice, we still have to choose this carefully. So returning to our model, we can also write this 4th and final point for optimizing capacitance. All in all, therefore, capacitance depends entirely on the geometry of our conductors and the permittivity of our insulator. So we've come full circle. At the start of this video, we asked why we use parallel plates for capacitors and not other objects like charged spheres. And now we know why by showing the capacitance is not just charge divided by voltage. Instead, it depends on the geometry of our 2 conductors and the permittivity of the insulator between them. Capacitance is a fundamental property of nature, which exists any time there are two charged conductors separated by an insulator. And this happens far more often in nature than you might have thought. Capacitance exists between your finger and a phone touchscreen, between thunderclouds and Earth, and even just you and the ground. But even though we now know what capacitance is, there is still one mystery that we haven't really touched on yet. We know a capacitor stores charge, which leads to a field and voltage. But what about energy? Where does that fit into our discussion? Is the energy stored in the plates, the field, or even the dielectric itself? That's what we'll explore in the next part of this series. By the way, if you enjoyed this video and like testing your physics knowledge, you're welcome to check out the Decipher Physics app, which is completely free and has over 100 questions for you to work through. Thanks for watching.